Hey, thanks for tuning in today. We're going to talk about some probability again. These problems are what I call and problems. So in these problems, two events are occurring, two or more events are occurring. You're going to roll a die twice. You're going to draw two cards. You're going to, pick two people for a task, that kind of a thing. So multiple events are coming on, and often those events are connected in the language with the word and, which is why I call them an and problem. And the rule for and problems is for and problems, you multiply. That's the overarching rule. So if we put it kind of in some math language, if you have two events, so let's call those events event A and event B. So if I ask you what's the probability of A and B, the way that you do that is you take them each individually. So you're going to take the probability of A, and then you're going to multiply it by the probability of B. That's the game plan. So let's do a really simple example. Let's say I'm going to roll a die, and I'm going to say, what's the probability that I roll a 3 and then an even number? Okay, so let's remind ourselves what the sample space is, because the way I like to kind of lay this out is I draw two lines with my operation in between. And that reminds me that I'm doing two things independently. I'm going to multiply at the end of them. So I kind of write it out like this, here and here. The multiplication is happening because it's an and. And then these two lines represent the two activities. So the first thing I'm going to do is say, what's the probability that I roll a 3? Okay, well, the sample space for rolling a die is going to be 1, 2, 3, 4, 5, and 6. Those are my options for rolling. How many ways can I get a 3? Well, one way. Out of how many total? Sample space is 6. Okay, so that's the probability of rolling a 3. Then I go, okay, what's the probability of rolling an even number? Well, that's going to be 2, 4, or 6. So there's 3 ways I can get an even number out of the total 6. And then you multiply the two. Now, if you don't know how to multiply fractions, that's okay. Don't worry. You can do it on your calculator. If you're multiplying fractions on your calculator, please remember to put parentheses around each of your fractions. Otherwise, the order of operations will get messed up. So you're going to go parentheses 1 divided by 6 and parentheses times parentheses 3 divided by 6. And when you get that, that's going to be, you're going to get 3 out of 36. Or if we're in decimal form, that's not reduced form. Reduced form, that's going to be 1/12. And then 1/12 in decimal form is going to be 0.083. So either 1/12 or 0.083 is a fine answer either way. So here's what happens when, if you think about like if your answer makes sense or not. With an and situation, I'm dictating more parameters. I'm saying this has to happen and this has to happen. And so the likelihood of both things happening makes the likelihood of the whole scenario to go down. So what you're going to see is your probabilities are going to be lower typically in this section than they were in 3-1. Let's look, for example, if I just say, what's the probability of rolling an even number? Well, now you're 3 out of 6, which is 50%. You're 50% likely to roll an even. But because I add that constraint of and roll a 3, then that's going to make my probability go down now here to like 8%, which is significantly less. So the more and more parameters you put on, the lower and lower your probability is going to go on. So if you think about like playing poker or something like that, that's why the probability of getting like a royal flush is very small, because I have to get this and this and this and this. They're all these individual probabilities. They all have to happen. And when you multiply them all together, the probability is very, very low. Okay. So this is the basic strategy for AND problems. You're going to take however many events, you're going to multiply them all together. Now, if I have 5 events, that's fine. You're going to have 5 lines, multiplication in between, and just do probability of each of those events. Okay, so let me do another example. Let's say we've got a bag of marbles and I've got 3 blue, I've got 2 red, and 7 yellow marbles in the bag. So I'm going to draw two marbles. I'm going to draw one and put it back, and then I'm going to draw another one and put it back. So this is going to be I want to know the probability of first drawing a blue and then a yellow. Okay, so again, actually, let's do 3 events just because we haven't done 3, and another yellow. Okay, so the scenario is I pull a marble out, I want to get a blue, then I put it back in, I pull another one out, I want to get a yellow, put it back in, and then another yellow, put it back in. Okay, so this is 3 events right here. I've got 3 probabilities to fill in. I'm going to multiply all 3 of those together, and I go one at a time. What's the probability of getting a blue? Well, how many blues are there? There are 3 blues out of my total, which is 12, 7, 8, 9, 10, 11, 12. Okay, adding those up. So that's my blue probability. Now, what's the probability of getting a yellow? How many are there? There's 7 out of my 12. Okay, and then the last one, a yellow again, it's the same, 7 out of 12. So I'm going to multiply all those numbers together. Multiplying fractions, by the way, you just multiply straight across on the top and the bottom. So I'm getting 147 over, I've got a weird spot on my calculator where I can't read the number, so I just hit that, 1728. Okay, and if I divide those out, 147 divided by 1728, this gives me 0.085. Okay, so maybe round up to 9% chance of this happening. All right, now let me change the scenario a little bit. Same bag of marbles, but now I'm not going to put the marble back. Okay. So I'm going to draw this first marble. I'm going to get a blue, and then I'm going to set it aside. And then I'm going to draw a yellow, and then I'm going to set that aside, and then I'm going to draw another yellow. Now think about what's happening in the bag. You're starting here with 3 blues in the bag, 2 reds, and 7 yellows. 3, 4, 5, 6, 7. Okay, so that's our visual, right? That's what's rolling around in the bag. So I'm gonna first pull a blue. Now, this is still an AND problem. Listen, I still want a blue and a yellow and a yellow. So my setup is still the same. I've got 3 things. I'm gonna multiply them together. And when I look in this bag, what's the probability of getting a blue? Well, there's 3 blues. Okay, right here. 1, 2, 3 blues. So I've got 3 out of my 12. But what happens now is I grab one of these blues and I take it out of the bag. So now in my second part of my experiment here, I want to get a yellow. Now, how many yellows are there? There's 7, right? 1, 2, 3, 4, 5, 6, 7. So I get 7 yellows. But now what's my total? That has now changed because I took that blue marble out. I X'd that out, right? So now I only have 11 marbles in the bag. Okay, so my total changes because I'm not putting the marbles back in. Now I want to get another yellow. Okay, well, what happened? In the second event, I went in, I grabbed a yellow and I took it out. So now this yellow is gone. So now how many yellows do I have? I have 1, 2, 3, 4, 5, 6 yellows because I pulled one out the draw before. And how many total do I have? Again, decreasing by 1 because I pulled the one out and I've got 10. So the formula is the same. I'm still taking individual probabilities and multiplying them, but the totals are changing into different scenarios because in one I'm replacing and in one I'm not replacing the marbles. Okay. This is an illustration of what the difference is between what we call an independent and a dependent event. So let's write those terms out. An independent events are events that do not change each other's probability. Okay, so for example, if I roll a die twice, that's an independent event because what I get on the first roll does not affect what I get on the second roll. Okay. If I'm dealing cards from a deck, I'm going to save that example for later. If I'm drawing marbles out of a bag and I replace them in the bag, that's an independent event. If I'm flipping a coin, that's an independent event. My chances of flipping what I want on the first toss do not affect the second toss. My chances of guessing a test question correctly, that's an independent event. My guess on the first problem does not affect the second one. Okay. But when my action changes the sample space in some way, that's what we call a dependent event. Dependent events affect each other's probability. Now, a lot of times this has to do with replacement. That's not an exclusive way to tell if something's dependent or not, but a lot of times it does. Okay. So let's talk about a little bit more like kind of real life stuff. The probability of me owning a dog and the probability of me buying dog food are dependent. One is going to affect the other. If I own a dog, I'm more likely to buy dog food. Yes. Okay. That kind of a thing. So there's kind of some conceptual ways you can talk about independent, dependent as well, not just like drawing cards or something. But here's another dependent event. If I'm dealing cards, like we're playing poker, every time I deal you a card, I'm taking a card out of the deck. So that's going to be a dependent scenario because the card you get next is dependent on what you got first. If I dealt you an ace, then your chances of getting another ace are going to go down because there's fewer aces left in the deck. Okay. So that's the difference between independent and dependent. Now, let me just show you a little bit of math notation in case you need it. I tend to not use this too much in class, but the book uses it sometimes. If I have independent events, the probability of A and B happening is just what I wrote before, probability of A times probability of B. But if they're dependent, the way we write that is the probability of A and B equals the probability of A happening times the probability of B given A. That's what this vertical line right there means, given that. So B given that A occurs. So it's kind of a language way of saying A occurred and that affected B. Okay, now how does this flesh out practically? This thing right here, we're actually doing that automatically in the marble problem when we decrease these numbers. Okay, so in that sense, it's like, it looks like a different formula, but it's not really. You're just taking into account how your sample space changed. So sometimes what I'll say is for and problems, you multiply the events, but take into account if you're not replacing something or if something changes, okay? Another way that these problems can come up, these dependent problems, that's a kind of a different kind of language, is I could say the probability that a person owns a Ford, say a Ford, that kind of a car is, let's say 38%. So 38% of people own a Ford. Of those people, 3 out of 10 own a pickup truck. What's the probability that someone owns a Ford and it's a pickup? Okay, so in a sense, this is kind of two events, right? I'm like putting two requirements on you. It has to be a Ford and it has to be a pickup, but these are dependent events because there's, we're looking at the whole population saying 38% of those people own a Ford, but then we're looking at just the population of the people who own a Ford and saying 3 out of 10 of those people own a pickup. So my sample space changes. So these are dependent, okay? Now it's still going to be two events, okay, multiplied together because it's still an and problem. See that word right there? But I'm going to go one at a time and they're dependent. So I have to, my second probability has to be just related to that shrunken sample space, which it is in the language. Okay, so let's first look at what's the probability that somebody owns a Ford. Well, it says that 38% of the population does, and that's already in a percent form. So you don't have to build a fraction because remember how we talked about I can give you a probability as a percent, as a decimal, or a fraction, and they're all the same. So if I give you a percent, that's already built for you. It's not how many ways out of total, that's already divided out. So this is going to be 38%, only I wanted it as a decimal. So this is going to be 0.38. Okay. Now, the second one is what about a pickup? And the mathy way of saying it is what's the probability of getting a pickup given that, okay, there's that phrase again, that's that vertical line, what that means, given that they own a Ford. So with that prerequisite that they already own a Ford, what's the chances that they have a pickup? And that's what this sentence is saying. 3 out of 10. Now 3 out of is a fancy way of saying divided by. So this is like, this is your fraction for you. 3 out of every 10 own a pickup truck of those ones that have a Ford. And then you just multiply those together. So again, it's kind of like an intuitive adjustment that you make. It doesn't feel to me like a fully different problem because you're still just taking those two probabilities and multiplying them, okay? It's just sometimes one depends on the other. So for this, just to finish this off, I would multiply this out and I get 0.114. So roughly 11.4% is the probability of finding somebody that owns a Ford and it's a pickup truck. Okay. The other way that I can throw problems at you is in chart form. So let's say we have, we're looking at men and women. And we're looking at some degrees that people are majoring in college. Let's say some people are majoring in math and some people are majoring in English. And let's not make this too complicated. Let's just say some people are majoring in business. Okay. And let's say there's 11 people here, 12 people here, 10, 19, 17, and 8. Okay. Now I'm going to total some of these up for you just so it's easier. Our totals for the math, there's 23 people in math. So I'm just totaling all the men and women in math. There's 29 in English total. And there's 25 in business total. And then over here, we can total these here and figure out how many men and women we have. So we've got 7, 8, 38 men total. And then I've got 39 women. And that's 77 total people. Okay. Now I could say, what's the probability that I pick somebody in math? This is a simple probability, just one event. This is not an and problem. This is like from section 3.1. So I'd go, okay, math, how many people are in math total? That's going to be 23. Over how many people are we looking at? This total, 77. That's our complete total people. All right, so that's how the chart works. Now, what if we jump into an and problem? What's the probability that I pick two people, and I'm going to pick a math person and an English person? So say I'm like forming some kind of committee and I want to pick two people, and I want to know what's the probability that I'm going to get a math person and an English person. So again, this is an and problem. There's two, and we're going to multiply them. So I take them each individually. What's the probability I'm going to have a math person? Let's see, that's 23 out of 77. And in English, that's going to be here, 29 out of 77. And I multiply those together, and that's my probability. So let's see, 23 out of 77 times 29 out of 77. That's going to be 0.112. Right? Now, let me show you how this idea of given that or dependent things work in a chart scenario. I could say, what's the probability that I pick a math person given that they are a woman? Okay, now this is kind of a little bit different. This feels a little bit different because of this, how the chart works. All this is saying is this given that it's a woman just restricts my sample space. So remember how we talked about it before, like what's the probability I draw a yellow marble given that I already drew one? So my sample space is shrinking, right? What's the probability that I deal you an ace given that I've already dealt you 4 cards? So this idea of given that is just taking your sample space, which is the bottom of your fraction, right? Your total, and it's shrinking it. So what this does is it dictates your sample space. So what my sample space is just women. So look at what I'm doing in my chart. I'm narrowing the scope and saying, hey, we're not looking at the men. We're only looking at the women. Now, who do I want from the women section? I want somebody who's in math. So I'm going to that women's line there. I'm finding my math people. And this is going to be 12 out of my total women, not total people, out of 39. See how that happens? So it takes the whole table and it just shrinks you to look at one piece. Okay, let me do another one of these as an example. Let me see if I can gently clean this up a little bit. Okay, what if I want to know what's the probability of choosing a woman given that they are English majors? They're an English major. Okay, so again, the given that, whatever comes after that is what I'm shrinking my chart to. So I'm looking at only English majors. So given that is a fancy way of saying that it must be. So I want a woman that must be an English major. So I'm going to go up to my chart and I'm looking only at English majors. And then I want to know in that circled thing, what's the probability of me getting a woman? Well, there's 19 out of the total English majors, which is 29. So this is going to be 19 out of 29. Okay. So basically these problems are just kind of practicing that dependent part of the and formula and giving you an idea for like what this phrase of given that means. Okay. Ultimately, these are still like only one event probabilities. You're not multiplying anything because it's not saying picking a math person and a woman. It's saying just picking one math person, but it has to be a woman. Okay, so there's still just one event. We're not multiplying anything in this situation. It's just restricting your sample space, as opposed to this problem where it's saying, I want a math and an English person. This is two events. Now we're multiplying. All right, that should get you going on and problems, and I will see you in the next video.